All right. Okay, let's let's try again now that I remember to turn on my headset. Okay, somebody asked me about this. Um, so this is an integrand that shows up in the quiz, and this is the ellipse over which you're asked to look at this path integral here. So the question involved asking me if I made a mistake when I assigned this. All right, because if you look at the textbook, this path actually is a path from a different problem than the one in that this integrand shows up. I don't remember if it was a mistake when I did this or not, but this problem's fine. There's nothing wrong with it. Okay, so we'll take it at face value here. So the problem says you're supposed to use Green's theorem. Okay, and the answer is you're supposed to use Green's theorem. Because otherwise you're stuck trying to figure out how to integrate this expression over a parameterization of that ellipse. Maybe people don't want to do that. Okay, but the problem actually tells you to use Green's theorem, so you're supposed to do the area integral anyway. So let's figure that out. We have a double integral over region D, and it says that we're supposed to integrate this, and that's supposed to be equal to the expression above for the appropriate P and Q. P is y cubed, Q is x cubed, sorry, negative x cubed. All right, and so if we do P partial y, we're going to get 3y squared, and if we do Q partial x, we're going to get negative 3x squared. If I plug it into this, we're going to get negative 3 times x squared plus y squared, with the negative 3 factored out. Make sense? That's the area integral we have to do. Now, we're integrating over the region enclosed by this ellipse. I can rearrange this equation make it look like an ellipse. And in order to figure out what my semi-major and semi-minor axes are, I need to write it in the form x squared over a squared plus y squared over b squared equals 1. So it looks like this. We have our x and y axes here, and the ellipse looks something like this. For our axes. Okay, so I want to integrate over this region. Now, the naive thing to do is to imagine that I have two half curves here and choose this as my order of integration. Or equivalently, I could break it up on the other axis of symmetry, right? And integrate in the other direction. The way that I've drawn it is the dy dx integral. If we do that, we need the equation here for y, right? If we solve for this for y, we're going to get plus or minus the square root of 1 minus x squared over, we'll just write it as 2 here so it's not cluttered. Okay, so we have those top and bottom curves, and the outer limits are going to be from negative radical 2 to radical 2. Sorry, what? I'm working on it. Okay. This is what it looks like in this form. All right. Looking at it, it wouldn't be a surprise if I told you that this does not work out very nicely. Okay. Kind of becomes a mess. You get some integrals that you could do really, but you would end up being like beating your head against the wall doing trigonometric substitutions and other not fun stuff. Okay. All right. The same is true if we pick the other order of integration. If we go from -1 to 1 and use the solved for x version of these types of limits. Okay. Which, just to make sure that everyone understands what's going on, I'm talking about doing each of these half circles and going that way. We don't want to do that. Okay. But writing it in this form has given us a little bit of something that is valuable. We can try to figure out what's going on. All right. Now, as was mentioned in the audience, this looks like it's close to us being able to do something like a coordinate change, right? We would like to be able to do this in polar coordinates or whatever because that's way better. All right. The issue is this domain is not a circle, okay, or a segment of a circle. So we can't actually do that. But we did study some stuff in chapter 15 that's helpful. Okay? Because if I decide that I want to set x equal to the square root of 2 times u and y equal to v, then maybe we can make this work. Okay? If I set x equal to the square root of 2u, then I get the square root of 2u quantity squared here, right? And here I get v quantity squared, and that's still going to equal 1 because I haven't changed anything on the right hand side, and I get a new equation that says u squared plus v squared equals 1. What's this the equation of? It's the equation of a circle. Okay? So that means that this becomes this integration domain with u and v. Okay, I'm not going to take my time to draw a nice circle, but it makes it into a circle. The issue is that we have to make sure that we follow through on the appropriate aspects of that coordinate change. So, when we make a change of coordinates, it is necessary for us to compute the Jacobian determinant. I take the partial derivative of the original expression with respect to each of the partials, with each of the new variables, pardon me, in order to construct the scaling change that occurs when I switch to this new coordinate system. So we're going to have partial x, partial u, partial y, partial u, and partial x, partial v, and partial y, partial v. Looking at that new set of coordinates up here in the upper right, what's the derivative of x with respect to u? Derivative of x with respect to u. Radical 2. What's the derivative of this with respect to v? 0, right? Because there's no v's in it. What's the derivative of this with respect to u? 0. With respect to v? So this introduces a factor of the square root of 2. Okay? So when I make this coordinate change, this type of integral I substitute in my variables for x and y, and now I'm integrating over this disk. Okay? But I need to have Jacobian for that coordinate transformation. So it looks like this now. We are integrating over the disk where u squared plus v squared is less than or equal to 1. Negative 3 square root of 2u quantity squared plus v squared square root of 2 dA, except now this is in uv coordinates. Okay? So, essentially what we're doing is we're making an intermediary coordinate change to something that's nice, and then we're going to make another coordinate change to polar, because now this is easily representable in polar coordinates. Does that make sense? Okay? I'm going to factor out the negative 3 radical 2 part. We have this left as our integrand. And we want to switch to polar. Okay, the problem is that we have a slightly inconvenient looking integrand, right? We'd much prefer this just say u squared plus v squared. But we can fix that. Integral of a sum is the sum of integrals. Okay? Now we switch to polar. 0 to 2 pi, 0 to 1. We have the u squared part, r cosine theta squared. The u squared plus v squared part is r squared r dr d theta. Now, that's a doable problem. Negative 3 radical 2. Want to write this out so that we don't make any silly mistakes. We're going to have r cubed cosine squared theta plus r cubed dr d theta. We get an r squared here times this r that we have to distribute to both of those terms. Okay, we can factor out r cubed. The integrals separate. And now we can work this out. First integral is 1/4. That's easy to see. Okay, for the other integrals, we're going to need to have 1/2. So let me write this out. This becomes 1/2 1 plus cosine 2 theta. For the cosine squared part. When I integrate that, we're going to get theta over 2 plus 1/4 sine 2 theta, and then plus theta. We evaluate that from 0 to 2 pi. So we're going to get pi plus pi over 4. Or sorry, wait a minute, hold on. What am I doing here? Make sure I haven't made a mistake. Yeah, no, sorry. It's pi plus 2 pi. This should be like down here or something. All right, the whole thing, we have 3 pi times negative 3 radical 2 all over 4. We can simplify this to this. Dividing a factor, or dividing the radical 2 factor out with the 4 in the denominator. All right. So, makes sense? Okay, I know it was a little bit of a road to get there, but this is why we have these coordinate changes. Okay? The coordinate changes are here to help us in situations to where the problem's a little bit hairy like this. All right? Practically speaking, and this goes to when you're using computers to solve problems or doing things by hand, is that a very, very, very powerful technique is to change coordinates to a domain in which you know the problem is easier to solve. Solve the problem in the easier domain, and then, if necessary, translate back. Okay? I went to a presentation last week where I think I brought up the idea of airfoils and how streamlines and things are handled in order to do the numerical computations. Okay? The talk was literally about that. Okay? A friend of mine was defending their dissertation talking about an enhancement that they had made to the numerical techniques in order to be able to solve these kinds of problems. Okay? But the trick essentially is we have a problem, it's hard, we change the problem to a domain in which it's easier to solve, and then work that and then translate it back into the language that we need for other stuff. Now, I put too many. I only need a double integral here. Okay, so when we started this problem, we discussed the fact that it could be written in terms of other variables, right? Oh, don't do this to me. All right. Sorry, I have to write it the other way. Okay. Remember that decimal. That's going to come back. Oh, whoops, I forgot to switch the dx and dy. Whoops. Did I forget a 2? I forgot the 2. What's the matter with me today? Oh no, no, that's not what we want either. It's not where the 2 goes. Sorry. It's the really trolling me in terms of what's going on with the values here. Okay. All right. This way, Wolfram is smart enough to figure out the actual exact answer, which is what we got. Okay. We found it using coordinate changes and other manipulations, but we produced exactly that answer. Okay. And we've posed the problem here in terms of what it looked like before we did any coordinate changes. So this should make us very confident that we're correct. All right. And I remind you, this is a way to check your work. Okay. You don't have to rely on examples that are worked out step by step for you or whatever. All right. And if you're really focused on developing your skills, you should look at some of the medium difficulty problems that you can find in the textbook or maybe online or whatever. Don't have the answer sitting in front of you. Work it out and then check. Okay. These things are good. All right. There's a reason you don't have access to the internet on your tests. All right. But these resources are available for you to check out. All right. So we have a few minutes left, but we'll definitely have to change our plans a little bit. So we have 3 sections left to cover to finish out the semester. Okay. On the schedule today, we were supposed to talk about surface integrals. All right. I'm going to briefly introduce the idea. All right. And then we'll do a little bit of work with this because it will come up in the context of 16.8 and 16.9, which cover 2 of our sort of like they're the big major final Calc 3 theorems. All right, so we'll say this is an informal discussion of section 16.7. All right. So the idea is like so. We have some kind of surface. All right. And on this surface, we're going to be looking at some little patch. Okay. And this patch up here is going to correspond to a patch in our parameter domain. Okay. And the parameter domain is not x and y. It's technically u and v. But I obviously drew this as a graph, so x and y are probably okay. All right. You have to remember we're distinguishing between parameterizations and graphs. But we want to make the picture as easy to understand as possible. Okay. So there's a patch here. All right. Now, in this situation, okay, what I want to do is I want to be able to integrate over this surface using the parameterization given to me by u and v. Okay? In the past, we had something like an arc, and we talked about what it meant to integrate with respect to the actual arc length, right? Surface integrals are the analog for that as we move to higher dimensions. The formula for these expressions are based on the formulas that we talked about in the video addendum that I did to last lecture, where I covered the idea of measuring surface area. Okay, we had in the past, again, calling back to the arc length example, a way to measure the length of a curve by just integrating the function 1 with respect to arc length, right? We talked before about integrating the function 1 we talked about integrating a special integral that measures the surface area. All right. Now, the surface integral of the function 1 with respect to the surface is another way to do surface area. The expression for this would be the double integral over the surface S of our function of 3 variables, ds, that's a capital S. This is equal to the double integral in the parameter domain of the parameterization of f with respect to u and v times the magnitude of the cross product of r partial u cross r partial v dA. Okay? Now, written in less scary notation, this is going to be, well, I can't really write it that way. This is, we actually are going to have to compute the cross product here. There's no short form formula for it. Okay? So this would be x partial u, y partial u, z partial u, x partial v, y partial v, z partial v. Where x, y, and z are both functions of u and v under the parameterization R here. Okay, what this gives us is the analog to the surface, for the for the line integral type formula that we have, the path integral, and we can do surface area equal to this. Okay. Those two expressions are equivalent. All right, so when we return, okay, we will look into this, okay, and use this type of expression to hit our two sort of punctuation points for big theorems from vector calculus, okay? We're going to be doing a lot of work relating path integrals and surface integrals and area integrals and things like that. We already have Green's theorem, which is kind of a flat 2D version of this, all right? We have some ways to expand this into 3 dimensions, okay? And that is what our 2 ultimate sections are going to be focusing on. All right. Take care, everybody. Enjoy yourselves, and I will see you in a week.